Do a little bit of rearranging as soon as we get everything in here. First, I'll set up to share, and I'll share the PowerPoint. Okay, and I'll scoot this over as far as I can, and I'll also get ready to share the whiteboard because I know we'll be using it. And now I'll start moving things around to so we can be more effective in. All right, here comes Jalen. Okay. Well, let's see. I've been calling your name, so I've been forgetting to write you down. That was Manessa here. Jalen here. Macy here. And Mercy here. So Jalen, there you are again, the odd man out, the only non-M here. So let's see if I can get this tool taskbar out of the way. Hey, you can't see that, but I can, and it messes up my ability to write on the whiteboard. Okay, that's about the best I can do. All right, let's go back to, for the time being, the PowerPoint. Okay. I'd like to ask y'all to help me remember to make a fairly important announcement before class is over today. When we get as many people here as it looks like we're going to have, I do have a pretty important announcement from the the Vice President for Academic Services. Remind me of that so I can get that done. I don't want to forget it because it needs to be made today. All right. Any of the new folks that just came in, any questions, issues, concerns, problems before we get started today? All right. If not, we will set up from the current slide. And we're beginning today. Oh, by the way, let me ask you this question. Did everyone, I know at least one person was able to see the Chapter 12 test because that person's already turned it in. I was a bit surprised at that, but that it was that quickly. But did all the rest of you realize the Chapter 12 test is out there? That's test 3. Okay, good. All right. Just letting you know I did put it out. I guess it was last Thursday evening after our class. I almost panicked this morning thinking, did I get that out there? And I looked and checked and it was there. Okay, so today we're starting chapter 16 and the title is Wave Motion and Sound. Now, at least by the title of the chapter, this is probably the most important chapter for diagnostic medical sonography because it's dealing with sound specifically. Everything else that dealt with forces and energy and matter, that's all important. But this is the one dealing with what y'all will be dealing with, sound. But of course, forces and energy and matter is all involved in sound, so that's why you needed that kind of background before we got to this chapter. So there are listed here several 16.1 is characteristics of waves. Now, before we get to this slide, I guess we'll go to the whiteboard, okay? Because there's several things here that are not on that slide before we get to the slide. Okay, now there's several types of waves. We're going to be, or you're going to be most focused on sound waves, okay? But they're going to represent waves in a generic sense here, so you need to understand what we're talking about. Energy can be transferred by the motion of part. Oh, whoa, here comes Mika. Let me get Mika here before we get going much further. All right, Mika's here. All right, we got 5 here. I hope that's how many. Yep, 6 total, with me being the 6th one. Okay. And Mika told the others I have a fairly important announcement to make, but I want to get as many people here as possible before I make it. So just remind me of that. If anyone has to leave early, please stop me before you have to leave and say, hey, can we hear the announcement? That way I won't have to repeat it every time somebody else comes in. Okay. Say that again. Okay, I couldn't hear that well. Say it one more time. Oh, I see. Okay, so you want me to go on and make the announcement now? Okay, the one reason I was hesitating is I'm preaching to the choir right now. If my marking is right in my book, I think every one of you have completed your payment for the course. Now, if by chance my marks are not right and you have not completed payment for the course, then please do so. The Vice President sent this, it was in an email, but it's a memorandum that was attached to an email late last week. And he said, please call roll from your official class rolls each week. Well, I don't call roll. When people come into the class, I mark them in the book. Okay, so that's a little bizarre. He's acting as if we're still on campus. Oh, and here's Molly. Okay, let me get Molly here before I continue with this so everyone can hear. We're only now missing Devin, and he's been missing for a few weeks, so I don't think we'll hold off the announcement for him. Now, also, I don't see, yeah, I've got 6 students, yeah, so I think all of you are here. Okay, so here's the announcement. Okay, like I said, the Vice President sent this, and what he said was, please call roll from the official class rolls this week. Now that is assuming that we're sitting in a classroom and I call roll at the first of the class. Well, I don't do that, okay? As people come into the class, I mark you in the roll book. Okay, so we're going to have to make an adjustment to this. And it says if any regular term students in your class who are not on their official roll, which means you have not completed payments for some reason or another, then ask them to check with the business office, and there's a phone number here, or the financial aid office. Well, I've got a phone number for that as well. So if any one of you needs, for any reason, the phone number for the business office, I've got it, and also for financial services office, I've got that as well. Now, here's what he says in the memorandum. You should not allow the student to participate in class after tomorrow. That's Wednesday the 8th. And he tells us where we can get the official roll. Well, now that's a little, again, it's acting like we're in the classroom and someone's coming in. I say, no, you can't come in until you, yeah, I wouldn't do that anyway. Here's my take on this. Now, I don't know, all of you may have finished and completed all your payments, and if that's the case, preaching to the choir, okay? But if any of you even suspect that perhaps you have not completed all your payments, and I was told this morning in Student Suite there is a place you can go to see if your payments are complete. And I haven't checked lately to see, but way back, a while back, there was just one person in the class who indicated that perhaps they weren't completed with payment, and that person may have already completed payments by now. But if you haven't, please get in touch with either the business office or the financial aid office. Now I'm going to hold up these numbers so you can see them. There's the business office number, 205-929-6334, or financial services office, and that number is this, 205-929-3434. is that a 22? I think it is. Okay, so those are the numbers to call if you think or suspect or even have some sort of clue that perhaps you haven't finished all your payments. Please get in touch with them sometime soon, so that if they know you're in the process of doing that, they won't flag you to be removed from the class. That's the important thing, especially the business office. Okay, financial aid office, if that's what you're waiting on, then go through them. Now, here's what makes this a little ridiculous. If they really did not want students who hadn't paid not to be able to come to class, in this sense, all they'd have to do was remove them from the Blackboard roll. And if you're not in Blackboard, you wouldn't be able to see the announcement about the Zoom meeting, and you wouldn't be able to get in. They haven't chosen to do this, and they seem not to want to choose to do this. And I'm kind of glad, because I'd just as soon you be here. If you are planning to complete payment before the end of the term, I'd rather you be in class than not in class. Okay? Now, I know they don't like that. They like for us to be the bad guys. But, you know, frankly, if you're going to complete payment, I want you in class. Now, let me say this, the other side of that coin, where it sort of sounds like I'm the bad guy, and maybe I am, but it's just a fact of life. I cannot give a grade to a student who is not paid, because the only people we give grades to are people who are on the official roll. That means you've completed payment. So if you don't pay by the end of the term, even though you may have taken every test, you've done everything the way you're supposed to do, have an A in the course and all that kind of stuff, if you haven't paid, you cannot, I cannot give you a grade, period. So please get the payment completed so that you can get a grade for the course. You've worked at it long and hard enough that hopefully I want you to complete it. So please, if you haven't paid, get in touch with one of those two numbers to make sure they know you're in the process and what your plans are. If you have paid, you're made in the shade, so nothing to worry about there. All right, sorry, too much blah blah blah, but I did want to get that announced, and it is being recorded, so even if Devin comes in late, he can hear it there on the recording. So anyway, let's go back to wave motion. Any questions about that, by the way? Okay, all righty. Chapter 16, 16.1, characteristics of wave. Here's what they're saying. Energy may be transferred by the motion of particles. For instance, I rub my hands together, they get hot. Why do they get hot? Because I have friction on this hand, rubbing against friction on this hand. That's increasing the motion of particles, creating heat. Okay? That's particle to particle energy transfer. Okay? Now, electricity conducted along a wire is a movement of particles. Basically, electrons are moving there, and if they run into resistance, they give off heat. If they happen to hit a certain set of electronics, they may get off sound. They may give off light. They could run a TV or something like this. So yeah, that's movement of atoms and molecules. But energy can also be transferred by wave motion, and that's what this chapter is talking about. If you think about it, the sun is 93 million miles away. Okay, on this time of day it's that way. Okay, 93 million miles away, and yet the energy from the sun gets to us. There is no contact between the sun and us, not through 97 million miles of basically space. What transmits the energy from the sun to the earth? Wave motion. Okay, so that's what we're talking about here. You're hearing me talk. Now, why are you hearing me talk? Because when I speak, I have my larynx is contracting and doing the various things that it does as air is being forced through it. It's producing a pressure wave from air molecules. If you hold your hand in front of your mouth when you're speaking, you can feel the little pulses of air hitting it. those are sound waves. That's a pressure wave. We'll talk about that in just a little bit of time. But that then goes into the microphone, and through electronics here, it's converted to an electronic signal, and that goes through waves, through the internet, through whatever. I can't even describe all the ways that it does, and then ultimately gets to your speaker, which translates that electrical signal back into a sound signal. So your speaker on your computer, whatever it is then making a sound signal that again is a pressure wave. So that went through several different kinds of waves, okay? And they go into other mechanisms there a little bit. So I'll let you read the book on that. So let me hit, I think all of you have books, but just in case, let me go on and type in some of these, this terminology here, okay? Okay, we've already said, I guess maybe I should do this. Energy may be transferred by wave motion. I'll put that down. Okay, there's kind of the first sort of a point in the chapter. Okay, now that's on the bottom of page, whatever, I don't even see a page number here, 425. On page 426 near the top, what in the world is a wave anyway? Okay, now, this is going to be sort of a generic definition. Okay, a wave is a disturbance that moves through a medium or through space. That's what we mean by a wave. It's a disturbance, some type of a disturbance. When I was talking about sound waves, obviously I'm disturbing air molecules and making them compress, and the opposite of compression is rarefaction, and that's the disturbance, okay? And that's through air, the medium. That will also go through liquids, it'll go through solids. Sound goes through all three of the phases of nature, phases of matter, solids, liquids, and gases, okay? Now, when it's going through space, the disturbance obviously is not of a material disturbance, it's an electromagnetic field disturbance. And that's part of what's going on between when the sound leaves my mouth and reaches your ears. It has to have gone through electromagnetic disturbance as well for it to be broadcast through the internet and whatever. Okay, so that's what a wave is. It's some type of a disturbance that moves either through a medium or through space. Okay, now the figure 16.1 in the book is a rather idealized situation. And what it's talking about here, they're modeling, I'll let you see it in case you don't have a book with you today, they're modeling wave motion with masses connected by springs. And if you can imagine a situation like that, now that's sitting there very horizontal, and that's why it's idealized. It wouldn't. There'd be some sag in the middle if that was really the case, no matter how strong those springs are. But if you were to ping on one end, say mass A there, it's going to compress the spring right next to it, and then that's going to probably push B away. That compresses the next spring, and it sends the wave down that series of springs and the series of masses. That is a disturbance from your pinging on it. Or you could pull on it and release it, and that would send the opposite kind of wave down from one mass to another, and until it reaches E. Okay, those kind of oscillations are examples of material waves. Okay, now some more definitions. Okay, a pulse. is a non-repeated disturbance that carries energy through a medium or through space. Now that's what we mean by a pulse. And that's what I was describing before, the pinging on that spring setup, okay? Okay. That would be a pulse, a non-repeated disturbance, okay? Now, every little sound wave that I make is in some senses somewhat non-repeated, because the next one probably doesn't sound just like the previous one, okay? That's how you can make out different words and frequencies and other things like this. So those are the pulses, okay? Now, let's talk about those pulses. They have certain characteristics. And there's a couple of different types of waves they're going to mention here. And they start with, to me, the lesser important one, especially for this course, but let's go with it the way the book does. Okay, the first is a transverse wave. Is a disturbance in a medium in which the motion of the particles is perpendicular. We'll talk about what that means in a minute in case any of you don't know, to the direction of the wave motion. Okay, I hope I've spelled it all right. Okay, now this is where we're going to go back to the slide, the PowerPoint slides. Okay. Transverse wave is a disturbance in a medium in which the motion of the particles is perpendicular to the direction of the wave motion. Now, I got a little bit of a problem with that, because now they're making it sound like this is only when you're dealing with material waves. But no, this is also true for, and this is a little more esoteric here, the motion of the field is perpendicular to the direction of the wave motion. That would be if it's traveling through space. So this could be through space as well, but now they're talking specifically about material. But this could also apply to space. So don't think transverse waves only happen in materials. They happen in space as well. Electromagnetic waves are actually, they're a three-dimensional wave. One dimension's going up and down, the other is left to right, and I can't get my fingers to do that properly. And it's a incredible phenomenon, or that's at least how it's represented. Okay, so it doesn't have to be strictly material and in a medium or with particles, but we'll let that go for now. What do we mean by transverse wave? Well, let's go back to the book. I think they show this. Let's go back to the slide. Yeah, there is a transverse wave. Now, remember, a wave is basically taking energy, transferring energy, moving. It happens to be, in this case, a particle, but it doesn't have to be a particle. It could be a field, as in electromagnetic field, okay? Light, not sound, but radio waves, you know, all sorts of things. Those are field waves. Okay. Now, what is meant here, a transverse wave, you'll notice, now here's my best favorite example of a transverse wave. I can remember when I was a young boy, for some reason I found it really interesting. If we were doing something and we had the hose spread out across the yard, okay, if as long as my parents weren't using it or something like that, if it was just lying there, I like to go and get one end of the hose and yank it up and down just as hard as I could. And what would happen? The hose would have this snake effect that goes down the length of the hose. Now it peters out after a while because there's a lot of resistance there, okay? But I would do it as hard as I could, as high as I could, to see how far I could get that. I didn't know I was creating a wave. That's a disturbance that's going up and down like this. That's how I raised the hose up and yanked it downward. And yet the motion of the wave was down the hose. So the motion of the particle was up and down, but the motion of the wave was perpendicular to it. The energy transfer of the wave was perpendicular to the motion of the particle. And that's what we see here. The medium, the particle, the energy, the field, whatever it is, I mean, not energy, is going up and then down and up and down, but at the same time, it's moving longitudinally. The wave is moving this way. Okay, so some of the characteristics of this, the low point in that is called the trough. The high point is called the crest. The direction of wave travel is where it's moving from and to. That's the direction. That's a vector quantity. The arrow indicates which direction. The particles are moving up and down perpendicular to the wave motion. Okay, that's what makes it a transverse wave. Now, some of the waves that are like this, electromagnetic waves are like it, but it's not particles moving up and down. Certainly the hose on the ground, that would be a situation like this. There are many others that you could probably think of that the particle motion's like this, but the wave motion is perpendicular to it. That's a transverse wave. Okay, so let's go let's go back to our definition page on the whiteboard. And that's a transverse wave is a disturbance in the medium in which the motion of the particles is perpendicular to the direction of the wave motion. Okay, need to get my text key back. Okay, now do y'all like the blue, or would you rather I use a darker color? I don't have to use blue, it's just what the default is. Anyone have a preference? Blue's fine. Okay, all right, Blue's Clues. Okay, now that was very old, wasn't it? Okay, y'all probably don't even remember it. Okay, let's get the next term here, the amplitude. Oh, and by the way, water waves is another example of the water goes up and down, but the wave goes along the surface. You can tell by your fishing cork, if you ever do much fishing, if the boat comes by and makes a wave there, all the cork does is go up and down. That indicates where the water molecules are doing, but the wave is carrying the energy perpendicular to that. So that's another example. So let's hit another characteristic. The amplitude of a wave is the maximum displacement of any part of the wave from its equilibrium position. I lost myself. Equilibrium, they actually put in another term here, or rest position. Okay, let me get that strung out here. Okay, so the amplitude of the wave is the maximum displacement from any part of the wave, and that's the from there, from its equilibrium or rest position. Okay, let's go back to the PowerPoints here, and unfortunately I have to go back and do this every time. Okay, so this would be an example of an amplitude. The maximum displacement, this happens to be in the negative direction, there is a maximum displacement in the positive direction. This, by the way, this horizontal line here is the equilibrium or rest position. Okay, the particles that happen to be right here haven't moved, or they haven't moved lately. They're right at their rest position. The ones up here have moved up, but this one's moved up the maximum distance. That would be the amplitude, or this would be the amplitude, or that would be the amplitude. Always the distance from the equilibrium position to the bottom of the trough or the top of the crest. That's your amplitude of the wave. We don't talk about the things in between that, the maximum position. Okay? Now, let's go back to the definitions. And now I got to get my text back. Okay. A longitudinal wave well, that's ugly, isn't it? Tough word. That doesn't look at all right. Is that right? Longitudinal. I think that's right. Wave is a disturbance in a medium in which the motion of the particles is along the direction of the wave travel. Okay. All right. Now this is the second type of waves. You have transverse waves, but you also have longitudinal waves. And you see the difference. The transverse wave, the motion of the particles is perpendicular to the direction of the wave motion. Okay, can anyone hear me? You can. I don't know what happened. I know we do have a rain shower going on here now, so I don't know if that's messing with the waves or not. Okay, don't know. Sorry about that. Okay, so the this is falling off my pocket too. That might have something to do with it. It may have been bumping into the book. Okay, so the longitudinal wave is a disturbance in a medium. I knew I had to have some typos in there somewhere. There's a space, and there's only one I in this medium. Okay, in which the motion of the particles is along the direction of the wave motion. If you think back on our masses on springs, if I ping them in this direction, the wave goes down in that direction. If I yank on it in the opposite direction, the wave is still along the line of motion. Now, if I had pinged upward or downward on those springs, then this kind of motion would be transverse motion. This kind of motion would be longitudinal. Okay? Now, that's a bit bizarre sounding, but I think they have this in the next figure, but let me see. This is such a lousy PowerPoint, I can't ever remember where it is. That indicates, yep, it is here. Here is the example of a longitudinal wave in a spring, just like I was talking about. If that series we had before that I showed you the picture of, that was a longitudinal setup, and as long as you pinged along that direction or yanked along that direction, you would produce a longitudinal wave. However, and this is what we're doing here. Here the guy's stretching the spring, or the person stretching the spring, and then compresses it and pulls back. The compression, that's what it's called, the compression here, and when he pulls back, it's called the rarefaction. You don't have to know that term right now, but that's what it's called, where things are pushed together and separated. Compression, rarefaction, compression, rarefaction. Okay, if he does this, just do as a single pulse here, pushes in the direction of the wave travel and then pulls back, then that compression moves down the wave. Okay, that is a longitudinal wave because the direction of motion is horizontal and the wave travel is horizontal. Now these could be vertical as well, but this one happens to be horizontal. Okay, that is a longitudinal wave. Now, examples of that: sound waves are longitudinal waves because your motion, compressing and rarefacting the air molecules and particles, compressing them, rarefacting them, and it goes out from my mouth to the microphone or whatever is going to be received. If we were in a classroom, going straight to your ears, and those are fascinating, incredible devices of nature, your ear, and how in the world it does what it does. Okay, so that's an example of a longitudinal wave, and sound waves are longitudinal waves. Now let's get a few other terminologies here. Okay, let's go back to our whiteboard. Okay, and I've got to get the text back. No, where's the text? Okay, it's quit texting me. I can't say why. I don't know why this is the case. I don't think it's going to work to do this. I'm going to try it. I'll can that, can this, oh, and go back to the whiteboard this way. All right, now I've got to move everything around again. You can't see this, but all my taskbars came back in the way. So let me move them. This doesn't affect you any, but it does affect me. I can't see what's on the screen when these taskbars or toolbars are hanging around there right in the way. And I think my setup is okay. So let's see if I can get text back again. Yes. Okay, remind me next time if that ever happens again. I have to shut it down and bring it back up. All right, where were we? I think amplitude is next. Oh, we already did amplitude. No. The wavelength. Now, I can't type the symbol lambda. Okay, so I'm going to spell it out. I'll show it to you in a minute. Is the minimum distance between particles that have been that have the same displacement and are moving in the same direction. Now, okay, let's string that one out. Okay. Now, I'll show you what I mean by lambda. Okay. Okay. Where are you tonight? Okay. There we go. Lambda. This is basically it's a poor drawing, but it's sort of what lambda looks like. That's the lowercase Greek letter that stands for our L, lambda. It's a length. Notice length starts with L, the word length, and that's where they get lambda. The wavelength, lambda, is the minimum distance between particles that have the same displacement and are moving in the same direction. Now, you can do this with longitudinal waves, but it's so much easier to illustrate with transverse waves. So I think the next slide is going to illustrate that. But before we leave the one that we're on, I'll show you what we mean here. The wavelength. Okay, no, we can't really show you on this one because there's only one pulse. Okay, what we're dealing with wavelength is when you have multiple pulses. When you have, not just one compression and rarefaction. That's hard to do. So let's go to the next slide and it'll illustrate. But just to let you know, it is talking about a transverse wave. You could do the same thing with, if your maximum here was your compression, the minimum was the rarefaction, maximum compression, minimum rarefaction, maximum compression, then the distance between the equal point of your compression, first compression, and the next compression, that would be your wavelength. But it's so much easier to illustrate with a transverse wave. From peak to peak, from trough to trough, that would be, and that's what they mean by successive corresponding points in a uniformly, see, this is a uniformly repeated wave. That's what we didn't have on the last example. You could go from this point to that point, but you might say, wait, wasn't there a point at the same position here? Yes, you're absolutely right, except it wasn't going in the same direction. At this point, this one's going downward, this one was going upward. This one's going downward again, so that's your wavelength. From here where it's the same position, but also moving in the same direction. That's the wavelength. Up here, it's at the peak and going this way. This is the peak and going that way. This is the trough down here. Trough down, I said peak, crest, same type word. You could even use this point right here to this point over here. That would be one wavelength. Even though there's one at the same position here, that's going in the opposite or a different direction. So that's what a wavelength is. There's the lambda, a little bit better than mine. That's what represents a wavelength. Okay? Now, we're going to come right back to this in a minute, but let me give you the next definition here. And that will be on our whiteboard. Okay. Let me get the text again. And okay. The period is the time required for a single wave to pass a given point. Okay, pretty simple definition there, it sounds like. This is the period. Okay. The time required for a single wave, my internet connection is unstable. I don't know if you can hear me. Did I get garbled or anything during that time? Okay, good. Well, I got a flash on my screen saying my internet signal was unstable. And actually earlier today I couldn't even print or do anything from this computer. Well, no, get emails or anything from this computer because the internet. But that was right before we had a rain shower, and we got another rain shower now. I'm kind of glad we got a rain shower now, because I was supposed to have gotten the grill ready today if it wasn't raining at 4:45. My wife asked me to do that before she left to go to work today, and I got busy with stuff. And at 5 o'clock, when I was getting ready, or a few minutes before 5, I thought, whoops, I didn't get the grill ready, but it had rained a little bit earlier. I said, well, it may rain again, and sure enough it has, so I'm in the clear now. Okay, even though it's raining. So sorry about that. The period of time required for a single wave to pass a single point. Now, a wavelength is a distance between similar points. The period is a time between similar points. So one's a length and one's a period, a time, okay? The period is a time, okay? Let me go on and give you the next definition here, because it's so closely related, and that is the frequency is the number of complete waves passing a given point per unit time. Okay. There is whoa, I didn't capitalize the. Okay. I'm not used to this keyboard. It's sometimes too sensitive and sometimes not sensitive enough. Okay. The frequency is the number of complete waves. I thought that didn't feel right when I was typing it. Waves passing a given point per unit time. Okay. Now, here's what I want to point out to you now. The period is the time required for a single wave to pass a given point. Or in other words, the time per wave. For a single wave, time per wave. Whereas the frequency is number of waves per unit time. And guess what? They're completely reciprocals of each other. And that's going to be key, and we'll get to that in a little bit. Okay? Now, I don't think I'll do the next thing. I'll just read it to you. The symbol for frequency, the unit for frequency is hertz. Okay? Maybe I will do it. Okay? Let me get my... Okay. The common unit for frequency is the hertz oops okay, which is 1 oscillation per second. Okay, now again, let me refer to these things. The period is just a time. Okay, there's no special unit for that except seconds. It's seconds per cycle. Cycle is 1 wave. Okay, the period is seconds per cycle, whereas the frequency is cycles per second, oscillation per second. That's what a hertz is, Hz, named after Heinrich Hertz, a German physicist. They give his lifespan as being 1857 to 1894. Sounds like he only lived about 37 years, and yet he was very prolific, very great scientist. But he did some of the early studies with frequencies, and so they named the unit after him. Okay. Now, we a lot of times don't refer to just the hertz. If you're dealing with anything that's very high energy, any kind of high energy, often things are kilohertz, which means thousands of hertz, megahertz, millions of hertz cycles per second, gigahertz, those are billion cycles per second. That's a gigahertz. Okay, radar and microwaves are measured in gigahertz. Your FM radio and your TV are usually in megahertz, and your AM radio is typically in kilohertz. Okay, just to give you those those relationships. Now, let me now use the screen here because I can't, well, I sort of could do it. So I'll type it in. This will be the last thing we do here, okay, on this screen because I'm running out of room. The symbol for frequency is F, little f. And little f is equal to 1 over, how that came out, 1 over the period. Now the period, since it's a time measurement, we usually use capital T. In other places in physics, capital T stands for temperature. Most of the time in physics, a little t will represent time, just the general thing, time. How long did the ball roll down the ramp? Okay, that's just a little t time. But when we're talking about the period, which is a time for a single wave to pass a given point, that's a period. That's given the symbol capital T. Okay, capital T is measured in seconds. Frequency is measured in per seconds. That's what a hertz is. Okay, and in terms of units here, then let me refer to this. I think I'll just skip a few spaces here and do a hertz. That's a unit. That's a frequency. Is equal to a 1 over second. Second is a unit. Now, these are the parameters. Little f is frequency. Capital T is period. Hertz is the unit we use to measure frequency. Cycles per second. And seconds is what we use to measure your period, in seconds. That's a pretty important correlation there between the formula and the units. Okay, now another way that sometimes, and I'll just give it to you because you'll see it occasionally like this, we'll also refer to that as a second, and I can't do a superscript here, so I'll do this to the first to the -1 power. Okay, that's a way to express 1 over second, is second raised to the -1 power, and you'll see that. Let me write it in here as well. I'm going to scoot this down a little bit because we don't need it out here, and let me get my pen and draw it. Okay, the other way you could refer to this, and let me see if I can find, there it is what I'm trying to say here is second to the -1 power. That's what I meant by that. Okay, that's another way to refer to a hertz, is a second to the -1. Okay, now one more definition, and I just don't have room for it on the slide here. So what I'm going to do is come up at the top and do it. Let's see if I can get text back again, and let's see if we can get one in here. Okay, the propagation velocity okay? And that symbol is V of a wave is the velocity of the energy transfer let's just stop there, okay? I'm not even sure I can get all that on one line here, but let's see if we can. Okay, it's not messing up too badly there. The propagation velocity of a wave is the velocity of the energy transfer, okay? What they go on and say in the book, and is given by the distance traveled by the wave in one period, distance traveled in one period divided by the time of that period, okay? So basically that gives us a brand new formula. Now I'll write that in this way because I don't have room to do the drawing anymore. I mean to do the typing anymore. So let me give you that formula. Okay, let me get my pad again. Okay, and what this is velocity V is equal to the lambda, that's the distance traveled in one period. Distance divided by the period. Okay, that's your figure. Well, they don't have a number by it, but it's in your book near the top of page 428, just underneath the one that we have down here. That's just a couple lines above this one. Now, because 1 over period is frequency, you can also express that velocity as lambda times the frequency, because frequency is 1 over period. Okay, now for some reason, and you didn't, I've been told by other classes they can't see what just happened there. My hand hit a button and what I just typed got erased. I don't know why, so sometimes that'll happen. Point it out to me if it happens. So the V here is velocity or propagation velocity, lambda is wavelength, capital T is period, and F is frequency. Okay, now those relationships apply to sound, water, light, all kinds of waves. Okay, you just have to define what you mean by the wavelength, the period, and 1 over the period is frequency. So you got that relationship. So let's do example 1. Is it all right to clear this slide? Can't bring it back again, so it's okay to clear? I hear no objections, so I will clear it. Okay. Here's example 1. Find the velocity, so that's what we're looking for, velocity. That's the unknown here. Of a wave with a wavelength. What was wavelength? That was our lambda of 2.5 meters. Now that is one long wavelength. Okay. 2.5 meters. And a frequency of, that's your F, 44 hertz. And that's a pretty low frequency too. 44 hertz. And remember, a hertz is a per second. Well, what is your velocity? One way is distance over time, which would be wavelength over period, but since frequency is 1 over period, the other definition for that would be lambda F. Wavelength times frequency, and that would then be 2.5 meters times 44. Now remember what a hertz is? It's a per second. Okay, so what we do here, We multiply the numbers because that's what they're done, multiplied. And let me see if I can get my calculator free here. Should be able to do that in my head, but it's too late in the day. I don't really feel like doing it. Let me get my calculator set up here. 2.5 times 44 equal 110. So is that what y'all got to? 110, and that would be meters per second. Yeah, aggravates me when it does that. Meters per second. 110 meters per second. That sounds like it's going pretty fast. And it is relatively fast, okay? I can't go 110 meters a second. That's more than a football field. That would be like from one end zone to the opposite goal line. Okay, that would be actually, yeah, that would be pretty close to 110 meters in a given second. That's pretty fast. Okay, and that's what they got in the book, 110 meters per second. And by the way, only two significant digits here. Okay, because 2.5 only has 2, 44 has 2, so only the 1 and the 1 are significant. We do not put a bar over that 0 because that 0 is not significant. We have to have it there because it's 110. Okay, now the next concept we're going to hit, okay, is the idea of superposition of waves. So I think what I'll do is go back to my whiteboard. I'm on the whiteboard. Let's see. I think I'll clear this screen and start typing again. Okay. So let's get the text box. Okay. And we'll start right over here. Okay. Let me set these things down. I'm really careful. I'm trying to be very careful with that stylus because those things are expensive and I don't want to drop it and break it. The last computer I had that had one had it permanently tied to a string, so I almost couldn't drop it. Never did. I used 2 of those for years and years. But this one is free and I have no way, there's no place to attach it, so I can't do that. So let's hit a couple more titles here. Okay. When 2 waves of a similar type pass through the same medium, a new wave is created by the superposition of the waves. Okay. Now, sort of a lot of blah, blah, blah there, isn't it? Let me string this out so we can get as much as we can on the slide. Okay. Let's see. I think they've got a figure that shows that. Let's hope they do. Otherwise, I'll have to hold up and show you the thing in the book. Okay. Okay. That was our wavelength. Here we have it. All right. Here we have one wave. It has a wavelength here. So it has a shorter wavelength than this one. Now get this, folks, if it has a shorter wavelength, it must have, and it's going through the same type of wave in the same type of medium, that means it must have a higher frequency. And here's why. The wavelength obviously is shorter, but the wavelengths per displacement, that would be, this is almost 2 displacements in the time it takes 1 displacement here. In fact, I'd say it is a 2 to 1. Okay? Yeah, we see that later. So it's twice the frequency because it's half the wavelength. That's the relationship there. Now, if you have both of these going over there, then the particle displacements add. So right here at this same time here, they're both sitting at 0, so the sum is 0. This one goes up a little faster than this one does, but they're both going up, so this one is the sum of this distance up plus that distance up, so that gets you up to here. Okay, so every one of these is adding. When this is at its crest, okay, this is not quite at its crest, but it's still pretty tall, and it's still going up because this one's going up faster than this one's coming down. So therefore it reaches its crest here, somewhere in between this crest and that crest. Because now this one starts falling, and at the time that it passes, it passes here, somewhere right in here is its maximum, and then after that it starts decreasing because this one's falling faster. Now this one starts decreasing, so you have the trough of this one, which is where this one, but you see before you can get any lower here, this one starts going up, and there they meet at the same point. The sum is 0. Okay, here they meet at 0 because this wave up here is exactly the same but in the opposite direction as this displacement here. So you have what I call a node here, okay, where the displacement is 0, okay, and then you have another mini maximum here before you have your maximum minimum here, where now they both are below the line in troughs, and the trough for this one, the sum, is in between those 2 troughs. And then you go back to a maximum here, and then a mini max min here and a mini max here. I'm making up those terms. This is your superposition of those 2 waves, would be this wave. Now it's obviously a wave. It has its wavelength would be from here to there. Now that looks awfully close to, and it may be exactly the same wavelength as this one. I can't tell that for sure, but just looking at it. It also would be measured from here to there, because those are 2 points in exactly the same position going in exactly the same direction. Or from here to there. That would be another measure of your wavelength. Okay? But it's not from any old max to any other max. It's from an equal maximum. Okay? So there is your superposition. Now, they have another couple terms. I'll write these down when we get back to them. This is where you have what they call constructive interference. The waves are building on each other in a positive way, so you have your maximum of your superimposed wave here. Down here, you have this wave canceling out that wave. So here is destructive interference here. Here it's 0, there it's 0, and in here it's negative. They are defeating each other. This is a little bit of constructive interference here. Here is destructive interference here all the way to there. That's destructive interference. Then you have constructive interference, destructive, constructive, destructive. So that's what goes on here, and that's your peaks and valleys of your superimposed wave, superposition wave. Okay? You add the individual displacements, which sometimes is subtracting if one's positive and one's negative. Okay, so let's go back to our definition slide on the whiteboard and give you the definition of constructive interference. occurs where the waves add together to form a larger displacement. I'll just end it there, okay, because they're referring to a figure that we can't see. It's the one that was just up there, like point A. That's the maximum constructive interference was there. But anywhere between the two nodes that we had, okay, all right. Whereas destructive interference occurs where the waves add together to form a smaller displacement. Okay, I'll end that one there. Okay. Okay, don't know what happened there. Okay, destructive interference occurs where the waves add together to form a smaller displacement, and that was the figure B that we had before. Okay, now next kind of subtopic here is when we have a standing wave. Now that's sort of an interesting kind of concept here. So let me give sort of its definition. Okay. The wave displacement are constant and remain fixed in location. That's the definition of a standing wave. This isn't a really good sentence here, but I'm tired of typing. Okay. The wave displacements are constant and remain fixed in a location. Okay. I hear our dog doing something on the stairs. That must be my wife's home. Okay. The wave displacements, when they are constant, when you have superposition of waves, but the wave displacements are constant and remain fixed in location, that's what we call a standing wave. Now, that's sort of hard to demonstrate. I have this question I think I've asked before, and I'll ask it probably several other times. Have any of you ever been to the McWane Science Center? Yay or nay? Downtown Birmingham. You have? I don't know if it's still there, but at one time they had a little display over in sort of one corner there that it was in the dark, and they had a strobe light going at a pretty rapid frequency, and they had, you could ping on a very tightly held string there. You set up a vibration on it, and what they had, the strobe, it was in the dark, the strobe, and they would spray a mist so that you could see the wave in the mist. Okay, this is all really weird, a bad description, but it always looked like the wave was just standing there. It was actually vibrating like crazy, but the nodes were always in the same place, and the maxes and mins were always in the same place. That's what made a standing wave. Now, a more practical illustration of that would be, are any of you musicians? Guitar, piano, any kind of stringed instrument? You may not think of A piano is a stringed instrument, but that's what it has inside of it, are strings. Any of you? Yeah, this class, I never can get any musicians in this class. I'm not a musician either, but I can sort of understand this. But if you picture, you've seen people playing a guitar. They put their finger on the fret and pluck one of the strings, and it's fixed at this end. And when they pluck it, then that automatically sets up, you have two notes that are fixed in place. And if they hit the note well and it sounds good, then you have a certain number of fixed vibrations in between those two fixed points. Of course, if you go up a fret or down a fret, you go down in frequency or up in frequency because you're making the wavelengths different. Okay, that's what's happening with a fixed wave, a standing wave. Okay, now I think they have a figure of that, so let's see if we can get back to that so you can see what that standing wave looks like. We'll go from current slide, if I can get this to go to it. Okay, there's illustration of superposition of waves. This is now, it's a little bit of what you need to get to before you can talk about standing waves. Remember when we talked about a transverse wave traveling down? This is my hose on the ground here, except it's not on the ground, it's along a tightly stretched spring, and what I'm going to do is pluck it upward. Okay, sort of like you would a guitar or banjo or something like, pluck it upward, and that wave travels down the incident wave, they call this. If it hits a fixed location, it actually inverts and comes back as a reflected wave, and then it travels back in the opposite direction. Okay, now if you had a series of these, one after another coming in, okay, and then they reflect and go like this, then you could easily set up with, if this return to the normal here is exactly where that one is, then these two pile on top of each other and you get what they call a standing wave. Okay, now they go into a lot more detail than what we're going to do here, but this is illustrating this. Let's say that you're fixed at this end, you can tell you're fixed there, and you happen to be holding your finger on the fret here. If you do one big pluck here, then this represents exactly half of a wavelength. This length here, capital L here, is exactly 1/2 of lambda, because that only shows one, and you can call that crest there, with no troughs. You've just gone from one node to the next node. That's half a wavelength. If it goes one crest and then follows that by one trough and goes right back here, that's a standing wave where you have your length there is one complete wavelength, and it'll be reflected off here and go back in the opposite direction. They didn't show the reflection here. That would have just gone back here like that. I don't know why they didn't show it, but they didn't. Here we have another nice case of a standing wave. This is where you have 1.5 wavelengths, lambdas, in that one length L. Okay, and here you would have two wavelengths. There's one, and there, your wavelength. Yeah, sorry. Okay. My wife just got home, and anytime she's home, I have to have the door closed, okay, because I'm too loud. Okay, so that's what that little pause was about. Okay, so that just illustrates 4 different standing waves you can get from the same 2 points, where you have half a wavelength, a full wavelength, 1.5 wavelength, 2 wavelength, 2.5, 3, 3.5, 4. You could just keep going up, and those will give you different frequencies because they have, let's assume that everything's going at the same speed. You now have, this would be twice the frequency of this one. This would be twice the frequency of that one. This would be 3 times the frequency of this one, 1.5 times the frequency of that one. So you see how the frequencies vary according. And these are your standing waves. Now, I'm nowhere close to this. I don't even measure, but for someone who has what they call perfect pitch, in other words, your guitar is tuned to be exactly the right key, then your wavelengths are all going to be these perfect waves, okay, standing waves. Now, they do a lot of talking about it, now they leave it. Now, I mentioned strings instruments. If you have a horn, a flute, anything such as that you're blowing through, what you're doing there is you're setting up waves that go through there, and by pressing the different stops on that, then you're creating different frequencies, okay? And that's sort of what is going on here. You also, it doesn't have to be a stringed instrument. Your wind instruments do the same thing, and that's what the keys, that when you're playing the instrument, that's what they're doing, is adjusting the lengths, the wavelengths that you have. Even your percussion instruments would have, that would be drums, cymbals, and things like this. If you're following a xylophone, you know the different notes there are represented by different lengths of bars there, that when you hit, they make different frequency sounds. That's how you do your different wavelengths on those. Okay, so all instruments pretty much use that, and people's voices use that as well. Okay, now let's move to the next sort of subtopic here, and this is interference and diffraction. Now, we already talked about interference to some extent when we talked about constructive and destructive interference. That was a couple slides ago. But now we're going to talk about interference and a concept they call diffraction. And let's see which is going to come first, the slide here or the verbs. Well, let's look at the slides here first. Okay. Here we have two sound sources, let's say. And this one's producing waves in water, say, that are going, or this could be vibrations. It doesn't have to be sound, any kind of vibrations. And it's creating a trough here, a crest here, a trough there, a crest here, a trough there, a crest here, a trough there, a crest here. That wave is moving outward. This one's doing the same thing. Crest, trough, crest, trough, crest, trough. But what happens here, at these places here where you see the two crests collide, you have these the bright areas here. Where the nodes collide, that's where you have the everything going to zero. Those places where in the standing wave where they don't ever seem to move at all. And then the next place is going to be more crest and trough. So here is your line of nodes, they call it, where the see what they have here. Let's just say the red is a crest for this one, and blue is a what they're showing here. If those are the lines of nodes, blue would be a trough for this one and a crest for this one. And where they cross, then you have your nodes. Nothing's happening. If they're same frequency and everything else, same amplitude, you have deadness there. And that's what these radials look like here. Those are the actual from a tub of water, and these are the line of nodes, you'd say. And in between there, you have either constructive interference or destructive interference, but right there at the nodes, they are zero interference. They're canceling each other out. That would be the places of destructive interference. Okay. Now, they mention that, and they tie that in with and move it to this kind of a thing. Okay. Now, this is showing up a little bit later. Okay. So let me get a few definitions before we come back to this one. So let's go back to, how are we doing on time? 2 minutes. That gives me time for maybe one more definition here. Okay. All right, so let's go to the whiteboard. And I've got room on this, so let's go back to text. And I've already given on the earlier one, the interference one. Here's diffraction. Here's what we mean by this. Diffraction is a property of a wave that describes its ability to bend around obstacles in its path. Now, another sort of blah 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 definition. What do we mean by all that? Okay. Diffraction is the property of a wave that describes its ability to actually bend around obstacles. That's a pretty ugly obstacle, isn't it? C-L-E-S, not K-E-S. Okay, obstacles in its path. Okay, and that's what I think this next slide was showing. So let's go back to the slide real quickly here and see if we can get that shown here. Okay, now you see, and this is what they're representing here. This is what they call a wavefront. Think of these as water waves coming in. These are the crests. These are the peaks of your surf, you know, coming in, and they're coming in straight from the ocean parallel to the beach. But before you get to the beach, you have two jetties sitting out here. Now this one comes in here and it just keeps moving at its regular speed, but this gets held up by the jetty. So now the wave front curves. That's diffraction, the bending of the wave front. So now it's going in sort of a semicircular looking front. Okay, and that's because basically the friction that's caused by these getting in the way of the waves just coming in strictly on their own, they get in the way, and this stops it in its tracks here and everywhere back there, but the wave front here keeps moving, and that bends the wave. That's what we mean by diffraction. Okay, and waves do that. All kinds of waves do that. And they may give a couple of other illustrations. There is actually, well, no, it's still a rendition. See, somewhat parallel waves coming in, but then when they go through the jetty here, then they get bent like this. And this is actually a pool, a wave pool that they have, and they've made that happen. This is actually a picture of water wave. That's an illustration of diffraction. Okay. Have any of you ever been, what is it called up north here, Point Mallard? Is it where they have a wave maker? And I think probably they have one out at Alabama Adventure, don't they? Or Splash Adventure, or whatever it's called now. They make artificial waves here by doing the same type of thing, kind of in reverse though, okay? And that's a human-made wave pool, okay, a simulated beach, and people get to practice, play in that like they're doing right here. Okay, now that pretty much wraps up 16.1. Okay, there are no homework exercises in 16.1, so nothing to worry about there. So we'll begin next time at 16.2. Okay, on page 433, and 16.2 has some problems with it, and that will be relating both to 16.1 and 16.2, but we'll wait until we do 16.2 before I'll assign those problems. 16.2 is a very short section, so we're going to get well past one section that time, and then we'll move on to 16.3, which is sound waves, which probably y'all are most interested in. But these are the basic foundations for getting to sound waves. Any questions, comments, reactions, responses, anything? Okay, a lot of blah, blah, blah today. We did have a few things we could work on, formulas and equations. We'll do more of those after 16.2. All right. Then I'm going to stop sharing with you because I don't like sharing anymore. And unless there's some comments or anything else, we will end the, whatever you call it, Zoom session for today. No comments? All right. Well, I'll be ending the meeting for everybody. We'll see you on Thursday.